Good afternoon, everyone. Welcome back to our VKC talk. My name is Gary Fong. I'm a PhD student at the University of British Columbia, studying inclusions in diamonds, and I'm hosting this meeting on behalf of the Diamond Exploration Laboratory at UBC. VKC is a series of seminars focusing on diamonds and kimberlites. Our goal is to bring academics and industrial professionals together. I'd like to acknowledge SRK Consulting for being a long-standing sponsor. There are a few Zoom housekeeping notes for today. For the audience, please keep your microphones and cameras off during the presentation to ensure a good quality of streaming. Today's section will be around an hour long. Please keep your questions until the end of the presentation, at which point I will facilitate a Q&A section. Our speaker today is Kira Musiyachenko. She earned her bachelor's degree in geology from Novosibirsk State University in Russia, where she worked in a high-pressure petrology laboratory studying microdiamond inclusions in tourmaline from the Kurchatov ultra-high-pressure metamorphic belt. She then shifted from metamorphic petrology to method development and ab initio calculations, joining a research group at the University of Pavia in Italy, focused on elastic geobarometry in host inclusion system, where she completed her master degree. In yet another 180-degree turn, Kira moved into mantle geochemistry and isotope geochronology for her PhD at the University of British Columbia, which she has just successfully defended. This diverse academic path highlights her broad interest in Earth system and has allowed her to develop expertise across a wide range of analytical techniques. Despite this, her favorite method remains fieldwork, combining hiking, careful observation, and sampling, with Raman spectroscopy a close second. Without further ado, we now invite Kira. The stage is yours.
Thank you. I'm going to share my screen in a second. Gary, thank you so much for introducing me. I'm so happy to see so many faces here. This topic was the focus of my PhD, and I've recently defended that, so it's a pleasure to share these results with you and to do so without a stress of a doctoral defense. Before I begin, I would like to acknowledge that this research was done at the University of British Columbia, which is located on the traditional, ancestral, and unceded territory of the Musqueam Nation, and I'm very honored and grateful to be the guest on this lands. So here is a brief outline of the talk, so we all have a sense of where we had it. I will start introducing a few big picture concepts, and then we'll briefly return to geochemistry classroom to refresh the ideas such as isochron dating and garnet geochronology, before talking about the specific challenges of dating mantle rocks. In the second half of the talk, I'll present my research results and show how these advances open up new ways of thinking about mantle evolution using a case study from the Siberian Craton as an example. Okay, so to set the stage, the focus of my research is the subcontinental lithospheric mantle, or SCLM, the deep, long-lived mantle reservoir beneath the cratons. Many of you work with this material every day, whether through diamonds, mantle xenoliths, or geophysical data sets, so I'm not going to introduce it from scratch. The Cratonic mantle has formed early in Earth's history as a residue after extensive melt extraction, making it compositionally distinct from the convective mantle all around it. I really like this figure showing the S-wave tomography beneath the African continent because it shows that the mantle roots literally look like roots. And these features that we see there, they reflect the regions of the mantle that are colder and more depleted, which gives the rise to the higher seismic velocities that we can map. This kind of mantle underlines all of the Archean cratons worldwide and is mainly composed of the refractory peridotite. So think olivine, orthopyroxene, sometimes granopyroxene, and garnet and spinel. So why do you even care about the age of the Cratonic mantle? We get diamonds from it and we're fine as that. The Cratonic mantle has existed since the formation of the earliest continents. We know as much from the rhenium depletion ages that tell us that extensive melting has happened in early Archean. And it is widely thought that that's the reason why Archean continental crust has survived to the present day. At the same time, this mantle was never completely isolated. Rather than being a frozen, inert root, it interacted repeatedly with melts and fluids, coming both from the convective mantle below and from the crust when the plate tectonic started. Its mechanical strength has also been tested through episodes of weakening, deformation, and partial erosion associated with tectonic and magmatic events. And yet, despite all of this, much of the Cratonic mantle persists. This persistence makes it an exceptional archive of mantle processes spanning billions of years, if we can determine when those processes occurred. So, this brings us to the central question: how do we actually date the mantle? If we want to study the least altered material, we rely on mantle xenoliths that are brought to the surface by kimberlites and basalts. Compared to the surface geology, the one on the left, that puts us in immediate disadvantage. We don't have the outcrops, we don't have stratigraphy or cross-cutting relationships. Instead, we work with those small spatially scattered fragments, often sampled so far apart in both space and time, and we don't even know about it. On top of that, mantle periodites like the classic chronometer minerals, like the zircon on the left, that often occurs in the crust that we can date with uranium-lead chronology really precisely and accurately. So reconstructing mantle history becomes a problem of extracting time information from very limited and indirect evidence that we have. The scientific community is very creative in that, though. Despite all of these challenges, approaches have been developed to extract the age information from the mantle rocks. One approach here in the middle deals with the whole rock, that's what WR stands for, reconstructing isochrones based on spatially related mantle xenoliths. So every point on the isochrone would be one whole rock that we need to assume is spatially and temporally related to the rest of them, which is already on itself a little disadvantage. Another powerful method is the rhenium-osmium chronology. That's the rhenium depletion ages I talked about before, and also rhenium-osmium isochrone chronology that can also be applied. However, the errors are slightly bigger, and there are some assumptions that come in with the idea of the model age on itself. Though this method is great, and that's what granted us the most age information we have on the Cratonic mantle. And then the third approach is and that's the focus of the talk, is the isotope geochronometry of the garnet. Garnet is a common Cratonic mantle mineral, common after a certain depth when the spinel is not stable anymore. And importantly, it records both chemical and chronological information tied directly to the mantle processes because we have both of those things from the same mineral. Garnet underpins much what we know about the Cratonic mantle in general. It provides the basics for the PT calculations and records the detailed trace element signatures related to all sorts of mantle processes. In other words, you can imagine garnet as a book that we already know how to read. We have all of that information in it. The only thing that we don't know is where to place this book on the shelf. I don't know why, but I really like this metaphor. Basically, what is missing is the concept of time there. We can interpret these chemical signatures, but we often don't know when they formed or how different events relate to one another in sequence. If we can link this garnet chemistry to age, we can begin to place constraints on what melting occurred, when metasomatism took place, and how cratonic roots were assembled and evolved through time. This is especially important because the other major mantle minerals, such as olivine or orthopyroxene, provide very little, if none, chronological information. So garnet fundamentally expands what we can learn from these rocks. Garnet geochronology in the mantle can be approached using several isotope systems, and it's not even all of them that I have here. Samarium is the classic one, lutetium hafnium is another one, and the newly coming up system is uranium-lead. All of those have been successfully used on mantle xenoliths so far. In practice, they tend to record slightly different processes. The uranium-lead ages of garnet, like in this cartoon on the left, they usually approximate the age of kimberlite eruption, reflecting the lower closure temperature for uranium-lead system and its high sensitivity to disruption. Samarium and lutetium hafnium tend to reflect slightly older ages. However, samarium also tends to have ages younger, closer to kimberlite eruption compared to lutetium hafnium. Lutetium hafnium shows particularly strong potential for dating mantle processes, all of them such as melting and metasomatism, because it is very robust against the diffusive recalibration. And we'll look at it in a second. So now that geochemistry classroom that I was talking about before, lutetium and hafnium are both the elements that can be found at the bottom of the periodic table here, We have lutetium being the last of the list of lanthanides, and then hafnium right next to it here at the table. One of the isotopes of lutetium, lutetium-176, with time is unstable and decays into hafnium-176 via beta decay. We know exactly how long it takes for lutetium to decay into hafnium. That's the half-life that we have for this isotope. And using this decay equation, that's the same for all of the isotope decay system, if we know the current isotope composition, meaning the amount of hafnium and lutetium in our sample, we can back calculate to the point in time where that accumulation started. And that's the main principle of the geochronology. What makes garnet so good for the system is that garnet naturally incorporates lutetium inside its crystalline lattice. And then with time, that's what's happening. The lutetium is slowly decaying into hafnium. Garnet doesn't like hafnium as much, so it doesn't naturally incorporate so much hafnium, making this value very low. But then this hafnium remains trapped in garnet, and that's what we can measure to back calculate the time where this accumulation started. To do that, we use the concept of isochron. Isochron is a line that's connecting the data point on the isotope composition diagram, where on the vertical axis, we have a ratio of our radiogenic hafnium-176 to a normal non-radiogenic hafnium-177. A similar ratio on the horizontal axis, we have lutetium-176, our radioactive isotope, to the hafnium-177, the same value of a normal hafnium that we have there. So if we start at time 0, which is marked as T0 right here, when the mineral assemblage forms. How it forms, it's a question for a different method, but we have our mineral assemblage forming at this particular time. At this point, all parts of the system are assumed to be in isotopic equilibrium. When I'm talking about isotope composition of the system, I mostly refer to this particular ratio. So the time of the forming of the assemblage, all of the different minerals that are part of this assemblage have the same ratio of hafnium-176 to hafnium-177. What is different is the parent-daughter ratio. So it's a ratio of lutetium to hafnium. It is different because those are different chemical elements and different minerals prefer one to another. Like garnet prefers lutetium to hafnium, so its ratio is going to be high. And clinopyroxene prefers hafnium to lutetium, so the ratio is going to be low. That spread is what is going to give us the good precision on the isochron later. As the time passes, some of that lutetium in all of the minerals start decaying to form hafnium. The ones that have more lutetium are going to form more radiogenic hafnium, so the position of these points is going to change more than the position of those points. Now, that brings us to some intermediate time T1 in the middle of it. What we see is that if we plot the isotope composition of all of the minerals again, if the system remained closed and everything remained in equilibrium, they're going to plot again on the same line. That is our isochron. At this stage, the slope is still very shallow, reflecting the short amount of time between T0 and T1. Let's move forward in time again. We go to T2, that's our final time, that's we collect the sample, grind it, dissolve it, and try to extract the H. What we have here is this slope of the isochron telling us exactly the time where the accumulation started. To build this kind of robust isochron, as you've seen, we need something to anchor it at the low parent-daughter ratio and at the high parent-daughter ratio. With the garnet-bearing samples, high parent-daughter ratio is easy. It's usually going to be garnet. And at the low end of the isochron, we're either going to have clinopyroxene data, or if we don't have clinopyroxene in the mineral assemblage, we can use the whole rock data, which is also going to plot at the low parent-daughter ratio of the isochron. So this method is great. It has been applied for decades for crustal origin of the garnet, really successfully. However, up until recently, we faced analytical challenges applying it to the mantle rocks. Some of those challenges are very familiar to you. One is a very small sample size. Working with the mantle xenoliths means that we have to work with whatever kimberlite brought to the surface. So if you're lucky, it's up to 5 to 10 centimeters. I've worked with a pebble-sized samples, really annoying, but that happens as well. On top of that, mantle garnet is really, really depleted in a lot of major and trace elements, particularly in hafnium. So we have very, very low concentrations of analyte. And we can't compensate for that by processing more of the sample because our sample size is small to begin with. And if that's not enough, we also have sample alteration. Those same melts that bring our samples to the surface, the kimberlites, they have very high hafnium concentrations. So if our mantle xenolith gets overprinted with that hafnium isotope composition of the kimberlite, the original information is basically lost. It's really hard to untangle it from then. So all of those challenges lead to the biggest challenge, the unknown behavior of the lutetium-hafnium system at mantle conditions. You may ask why, since we have been applying it so successfully to the crust. Well, because most of the geochronology, the isotope geochronology, relies on the concept of closure temperature that is tied to the cooling rates and is tied to the temperature itself. And as you know, the temperature in the mantle is way higher than what we have in the crust. And the concept of a cooling rate is not really applicable to the rocks that are sitting at 1200 degrees for billions of years. So the first three challenges can be overcome with a careful lab work. That's me being very happy working in the clean lab at the UBC. And the last challenge became the goal to sort out for my PhD research. So the whole processing of the sample, if you take away the tedious multi-steps of lab work, is relatively simple. We start with the sample selection and preparation. The selection is to choose samples that are least altered and least interacted with the kimberlite melt. And the preparation of the sample includes separation of garnet from cyanopyroxene and preparing the whole rock powder. To do so, I grind the sample in an agate mortar and pestle because I'm really scared of contamination since the levels are so low. And then I ground the sample to the size fraction of a mineral I'm interested in, and I pick it out away. So that way I prepare the aliquot of garnet, cyanopyroxene if present, and then I make a whole rock powder. After that, all of those aliquots get dissolved in the mix of strong acids, and the tedious lab process begins, where we separate lutetium and hafnium from the rest of the elements that belong in our samples. That entire process of picking the sample, preparing it, measuring, and getting the isochron for one data point, if I work back to back, takes approximately 2 weeks. The problem is, since we have a step of adding a spike solution before working in the lab, means that we do a little bit of a guesswork with the concentrations. Because of that, I don't process all of the sample at once, since before processing it, I don't know the concentration of all the elements. So to get a robust, statistically good isochron, we need to have at least 3, 4, better 5 data points, and each one of them is a separate aliquot that gets processed consequently. So to tell the truth, if I get a sample that I've never seen before and I need to get its age, it would realistically take almost 2 months to get it, which is not an optimal speed for the industry, I understand that, but we're still at the beginning of developing this method. And then obviously I can process several samples at once. The lab work is the fun part. That's how we obtain those concentrations that give us the age. But once we have that age, the most important question becomes what that age actually represents in the mantle rock. To answer that, we need to step away from the laboratory and think how the lutetium-hafnium isotope system behaves under the high temperatures of the mantle conditions. That's again the closure temperature that I mentioned already. In most isotope systems, we rely on this concept. Above the value of this closure temperature, the diffusion is really fast. So if you think about this radiogenic hafnium accumulating inside our garnet, but if the system is sitting at a really, really hot temperatures above that particular value, then all of the hafnium that's been accumulating inside the garnet is also being diffusing away really fast. Because remember, garnet doesn't really want to have hafnium inside. And only when the system cools down below that particular value, that's when the hafnium becomes trapped in the garnet and the isotopic clock starts. For the crustal garnet, that temperature has been estimated to be around 800 degrees. That's plus or minus 100, depending on the grain size and the cooling rate. But you can imagine that the mantle temperatures are way higher. And there is no cooling in the mantle, so that's also not really applicable. So the problem is that the only time the mantle rocks would experience that kind of rapid cooling is during the kimberlite eruption, which is geologically very recent compared to when the mantle processes we're interested in actually occurred. But we also know that we can obtain some meaningful ages from the mantle, and that means that lutetium hafnium ages cannot always be interpreted as a simple cooling ages, and we need to sort out a different framework to find and understand what they actually record. To do so, there are several factors. I already mentioned the temperature and the grain size, but another important thing to consider is the composition of the matrix phases, meaning what's around the garnet, and the specifics of the diffusion in the mantle, which can be quite different than what we have from the crust, for different reasons. To do so, to explore every single avenue that can influence the preservation of the ages, I worked with a very variable sample collection from different cratons. I've got samples from Jericho pipe on Slave Craton, from Udachne, Vostochne, and Obnažone pipes on Siberian Craton, and from Boltfontein and Boshov Road dumps in the Kapval Craton, courtesy of Maya Kopolova and Andrei Korsakov from Russia. So I worked with all of those samples. They're very different. They have very different composition and texture. And to work with them a little bit better, I grouped them in grouped based on those characteristics. So the first one is the group with no clanopyroxene. Those are the Harzburgites and orthoperoxenites, obviously garnet bearing, with a variety of grain sizes and textures. The second, it's a slightly more common kind of xenoliths when we think about the garnet peridotite. It's a coarse lertolite. So we have clanopyroxene, orthoperoxene, olivines, and garnets, more or less in equigranular texture. And the last group is a similar chemical composition. So we have all the same kind of minerals, but the texture of those is the texture of the sheared lertolites, sheared or mosaic porphyroclastic, when we have porphyroclasts of garnet, clanopyroxene, and olivine, and the background made of olivine neoclasts. So those are the three groups of samples that I worked with. The composition of the garnet in each group was also slightly different. I plotted them on the calcium-chromium diagram that's used typically by mantle petrologists to classify the garnet. So we have our G10 and G9 field with that line that's important to us. So all of my clanopyroxene free lithologists, the garnet from those rocks plotted at the high end of this trend, right on the border between the G10 and G9. The lertolitic garnets plotted predictably in the lertolitic field along this trend, with the sheared lertolite garnets having the lowest chromium concentration and the highest sodium and titanium concentrations of all of them. So now let's look at what are the ages that we obtain from those rocks. What does a geochronometry tell us? Here's the isochron compilation. So reminder again, the slope of the isochron is connected to the age. The steeper the isochrons, the older the ages. As you see, the samples define a very broad age range from the Archean all the way to Proterozoic, and not at all Proterozoic clumped around the Kimberlite eruption as you would expect. And these results also clearly show that the ages are not really random. Every group has its own eon for the age. We have Archean for the clanopyroxene free, Proterozoic for the coarse lertolites, and Phanerozoic really close to Kimberlite eruption for sheared lertolites. So they show that the ages are tied to the textures and compositions of the rock. So back to our thinking board, those two seem to be the major factors that are impacting the preservation of the age. So let's zoom in on the matrix phases and see why they matter. Back to the concept of closure temperature again, it relies on another assumption apart from the temperature itself. It relies on the assumption that there is an infinite sink for the escaping daughter isotope when it diffuses out of our chronometer phase. Putting it simply, it relies on the fact that when hafnium escapes from the garnet, it has somewhere else to go. But if you look at the matrix phases of the most refractory peridotites, they're going to be olivine and orthoperoxene. And both of those minerals have very low distribution coefficients with respect to hafnium, meaning that hafnium doesn't want to go to those phases, like they don't want to have hafnium. So even if the temperatures are normally above the closure temperature estimated for the system, and hafnium would diffuse freely within the garnet itself, it cannot leave that phase. We don't have any fluid or melt in the grain boundaries, because remember, very dry dehydrated mantle. And none of the phases around it wants to take the hafnium in. So the chronometer remains closed, the system remains locked, and the clock keeps going on, even above the supposed closure temperature. Everything changes once we introduce the clanopyroxene. As you see, clanopyroxene has a very comparable distribution coefficient for hafnium to garnet. meaning that hafnium would like to exchange between those two phases if it could, but that would lead to the ages of all of the lertolites being the age of the cumulative eruption, because that's the only time where they cool down to the closure temperature of the system. That means that we're missing something, and that something is this last factor to consider, the diffusion kinetics in the mantle. What it is that mantle is really, really dry. So even if the distribution coefficients between the phases would allow the exchange of hafnium between them, there is still this energetical barrier to transport the hafnium from one phase to another. That kinetic barrier can be suspended if we have a fluid or a melt on the grain boundaries that would facilitate this exchange. And you know what? When you have a presence of a planoperoxene, so introduction of a new phase, and a fluid or melt on the grain boundaries, at the mantle conditions, it usually means one thing, the mantle metasomatism. So, in the lithologies that have planoperoxene, the age that we obtain from lutetium hafnium system usually means the last time the system has interacted with fluid or melt. If we now step back and look at all the results together, a slightly more coherent picture starts to emerge. We have our planoperoxene bearing lithologies here that have already a sink for hafnium. So lutetium hafnium ages in these rocks are sensitive to the removal of those kinetic barriers. In other words, the introduction of a fluid or melt that enables a re-equilibration. In these cases, lutetium hafnium ages record the last metasomatic interaction experienced by that rock. In contrast, the Harzburgites and orthoperoxenites are lacking the effective sink. In those lithologies, lutetium hafnium system remains effectively frozen, and the ages instead reflect garnet crystallization rather than metasomatic resetting. So with that framework in mind, I will now walk through each group and show how the textures, compositions, and ages fit together. Let's start with our youngest group, the ages that record the kimberlite eruption. These samples display a mosaic pyroclastic texture, which is commonly interpreted as an evidence for fluid-assisted recrystallization under high strain. Compositionally, these garnets are characterized by low chromium and elevated sodium and titanium, pointed to a kimberlite-related metasomatic overprint. The lutetium hafnium ages obtained for this group place time constraints on fluid-induced weakening of the Cratonic mantle, likely associated with protokimberlitic metasomatism. Importantly, these ages are also consistent with the idea that deformation, metasomatism, and that azeotropic resetting were all part of the same event, preparing the pathway for the kimberlite to go up on the surface. The older ages require a slightly different process. So a large group of lertolites that yielded Proterozoic lutetium hafnium ages spans a really broad time interval, almost the entirety of Proterozoic. What unites the samples is the textural and chemical equilibration between garnet and the planoperoxene. This is evident both in the garnet major element composition, as we've seen it plots along the lertolite trend, and in the rare earth element patterns for garnet and planoperoxene. So the event recorded by the lutetium hafnium system in these rocks was likely the introduction of the planoperoxene and possibly garnet. We cannot say for sure. It was either full recrystallization of the garnet or introduction of the new garnet through carbonatitic metasomatism that brings the missing calcium into the system. In this context, lutetium hafnium ages reflect the timing of planoperoxene addiction and equilibration rather than initial formation of the garnet. Some samples, however, do preserve those much older ages. And that's the subset of samples with their Archean ages, represented by Harzburgites and orthoperoxenites. So despite the present-day absence of planoperoxene in this rock, garnet compositions show past equilibration and buffering by planoperoxene during the melt extraction. Therefore, the most likely interpretation for those Archean ages is that melt extraction from a fertile pyrolytic mantle that has just exhausted all the planoperoxene, and that's where the composition of the garnet stands at that point. However, we also need to consider this extremely high abundance of orthopyroxene and garnet in those rocks, because both of those phases require really big amounts of aluminum and silica. That gives us hint to a prior refertilization, prior even to those Archean ages, that had refertilized the mantle, giving it the potential of crystallizing that much orthopyroxene and garnet at once. Clues to that refertilization history are preserved in the one particularly ancient and depleted sample from the Siberian Craton. That's the case study that I'll focus on next for the next 10 minutes. So this is a fantastic sample from the Siberian Craton. It is quite big on itself. I would say it's at least 20 centimeters tall. And the really great thing about this is that it preserves two different lithologies smudged together. On the top here, we have a megacrystalline orthopyroxenes with garnet exolution lamellae. This part of the sample is just a scan. That's the natural emerald colors of the enstatite. Looks fantastic. And then this is how much garnet lamellae we have in those orthopyroxene crystals. And the bottom part of the sample is a Harzburgite with a small rounded garnet grains. So usually what we have in the mantle samples, it's really difficult to determine where garnet is a primary phase or it was introduced metasomatically. It's really hard to argue for one or another, but in this case, the texture leaves no ambiguity. We know that those garnet lamellae were exoled from the enstatite. That process happens via an exolution from a high aluminum enstatite protophase when it becomes unstable during cooling or pressure increase. And as a result, the exolved garnet here has inherited the rare earth element composition of a very depleted enstatite. Remember, enstatite has very low distribution coefficients for most of the elements, to be fair. And garnet that normally would like to incorporate these elements is left with nothing because it dissolved from an enstatite phase that originally had nothing. But the interesting thing about this sample is that garnets from both parts of the sample, both the fine-grained garnet here and then lamellar garnet on the top, have exactly the same U-shaped, really depleted rare earth element spectrum that is hinting to the same origin for both of those garnets, meaning that this garnet can be the product of the recrystallization of the lamellar garnet. But we need to prove that, because also those garnets have very different major element composition. The garnet in the Harzburgite part is more depleted in silica and in aluminum and magnesium than the garnet in the lamellar part, but it's more enriched in almost the rest of the elements. We have more calcium, more chromium, manganese, and iron in the bottom part of the sample. So it gives us a question, what actually happened with a sample like that? And honestly, having a sample like that with garnet on both sides of it and a really, really peculiar texture on one side gives an excellent opportunity to test the limits of our new method of the lutetium hafnium geochronology. Similar rocks like this have been described previously in literature from Kapval Craton and from Tanzania Craton, but none have been dated with this method and certainly not at the scale required to isolate different textual domains. The analytical challenge here was that extreme depletion in both lutetium and hafnium in both sides of the sample that made me process almost the entirety of those precious parts to get the age, and we pushed the method all the way to the detection limits. Despite this, we obtained the robust lutetium hafnium ages for both parts of the sample, showing that indeed the exolved part is at least 100 million years older than the fine-grained recrystallized part. So these results proved our initial idea that this part is a product of recrystallization of the exolved lamellar part and allowed me to reconstruct a sequence of events explaining or trying to explain how this composite rock formed. So making our Archean garnet. Originally, based on a textual and isotopic relationship, I'm proposing the following sequence of formation. First, we have this high aluminum enstatite phase that has existed in the mantle prior to this determined age. And then the garnet first exolved from the proto-enstatite during cooling and or pressure increase at 2,977 million years ago. Later, fluid melt has infiltrated that orthoperoxenite, triggering the local reactions. Why am I involving the infiltration of the melt? It is because the border between the two parts of the sample is very sharp. The partial melting to produce olivine from enstatite would have also explained it, but in that case, I would have expected a more gradual change in the border. Instead, this kind of boundary looks like a reaction boundary to me. So having the influx of a fluid or melt that would trigger local reactions and maybe also partial melting would explain this really sharp boundary between the two. and also the transition from orthoperoxene to olivine that happened because we have olivine in this side and this side is a pure orthoperoxene. That kind of transition loses in volume, so it generates more pore space that would enhance the further fluid or melt flow, making a positive feedback loop, creating sort of a dunite channel that is observed in the upper mantle. So similar process was involved here. And then while this was happening, the garnet lamellae, those elongated and energetically unstable shapes of garnet, were resorbed and recrystallized into more energetically stable and rounded grains. And that's what I assume the second age is here. And then the sample was entrayed into kimberlite, and the bottom part, being slightly more permeable than the megacrystalline top part of the sample, was serpentinized way more extensively. And that's what we have. Again, with the sample as the same as of the Archean samples, we must have this mantle refertilization happening before the first recorded age to give us enough aluminum and silica to form this proto-enstatite phase. So that's another hint of this process occurring early in the Archean. Okay, moving to the first part of the conclusions. These results that we get from all of the sample suite allow us to place garnet compositions into a temporal framework, linking their chemical signatures to specific mantle processes through time. In the Archean, the silicon aluminum enrichment led to that garnet exolution or formation of those orthoperoxene-rich lithologies with garnet. In the Proterozoic, the carbonatitic metasomatism introduced more clinoperoxene and maybe more garnet, producing those calcium-rich and slightly more chromium-poor garnets and lithologies. In the Phanerozoic, hydrous metasomatism associated with the deformation and cumulative activity generated those titanium and sodium-rich garnets. So together those trends reflect evolution from the enrichment to the carbonatitic metasomatism to hydrous metasomatism of the mantle through time. Okay, so to conclude the whole thing, lutetium garnet geochronometry can now be applied robustly to mantle xenoliths, thanks to recent advances that allow precise dating of very small and highly depleted garnet aliquots. Importantly, lutetium hafnium ages in the mantle do not represent just the colon or kimberlite eruption ages. Instead, they record either garnet growth or its re-equilibration during different metasomatic events, depending on the lithology and mineralogical context. As a result, Archean signatures can be preserved alongside much younger ages, reflecting variable degrees of equilibration controlled by matrix composition and the diffusion pathways. Taken together, lutetium hafnium garnet ages provide a new temporal framework for reconstructing the metasomatic and thermal evolution of the Cratonic mantle through time. Thank you so much for your attention, and I'd be happy to answer any questions.
Thank you, Kira. That was really great presentation, and you have a really cool sample that show the two generation of garnet, and you have a very nice story of it. So now we have 10 to 15 minutes of the Q&A section. Feel free to turn on the microphone and video to ask questions in the chat box. The floor is open. So I will start with the first question. So in terms of the sample preparation, as I'm working on inclusion of garnet within the diamond, and they're usually very small volume of it. In terms of sample preparation, if I want to do geochronology on my garnet, what is the sample requirement in terms of the volume of the garnet to for analysis?
Well, if you work with the garnet inclusions, that's not really my field, but I know there is a research group in Switzerland that work with that. They obtain fantastic results for working with just inclusions, but basically you do laser ablation on those. So
Right.
you're not going to be able to do solution because obviously that garnet inclusion size is way, way, way too small for the solution. You're not going to obtain anything. But I would suggest looking into the research of that group. I can look them up and send it to you. I've seen them present at the Kimberlite conference, and it was very impressive. But yes, that way you would work with a laser ablation rather than with a solution method.
Right, cool. And because I guess for even for laser ablation, I mean the spot size, it really varies of what result you want to get. But for lutetium hafnium isotope, I mean merging there is such a trace amount. So I guess you would have to get a larger spot beam size to get a sufficient amount of isotope for processing.
Yes, the sample prep and the whole instrumental setup then is really complicated and very advanced, but they do manage to get some data from those samples. The other problem is that to construct the isochron, you need several points. So if you do just laser ablation, one inclusion, it's not going to be enough. You're going to get one point, it's not going to constrain the line. So you'll either need to have another inclusion in the same diamond or several diamonds with inclusion and the means to say that they're all cogenetic. That
Right.
would require some extra like Raman petrographic study to do so.
Right.
Hi, Kira. Vladimir here. Very tedious work in the lab. Congratulations for you. I realize it, seeing that. My question would be just related to your research. It basically three data sets you were looking from different location, correct? How many data points you got from each set to come to those conclusions? How many samples?
Are you asked how many samples?
Yeah.
I had 5 samples from slave Craton, 6 samples from Kava Craton, and 5 samples from Siberian Craton.
Oh, okay. Thank you. Did you plan or did you planning to do any other crotons, like any other samples you have access to do similar job to get proof? Let's call it this way.
Yeah, no, I completely agree with you. That's not enough. Like, it's not statistically great amount for that. It's mostly was a method development. It would be great. I don't have any funding right now at the moment to keep doing that,
Okay.
but I would love to.
Okay.
Yes,
No, thank you very much for answering that because it's definitely great work. Thank you.
thank you.
And I have another question about so you mentioned about a refertilization event with in the
Yeah.
introduction of more pyroxene. So when you do the isotope, what the age that you get is actually the event of refertilization rather than when the garnet is originally crystallized.
Well, that refertilization is what let the rock have enough aluminum and silica in the first place to crystallize the garnet. So garnet crystallization, if anything, occurred after the refertilization in my mind. So you first have refertilization of the mantle that didn't even have enough aluminum and silica to crystallize that volume of orthoperoxene in garnet. And then after that, some other event occurred that the garnet crystallized. Like in the case of the exolution, the garnet crystallized via the exolution when the PT conditions changed. The other question is our ages are the minimum estimate of the age, meaning that whatever we get from lutetium hafnium also might have been the age when that refertilization occurred rather than when the garnet crystallized. Because the system remained, if we assume that the system remained closed, then that the composition was the same when the garnet just started dissolving.
Right, I see. So basically, the fertilization and the garnet crystallization are the same event, but there's a potentially metasomatism event which happens later on that will change the isotope signature. Right.
Yes, that's the subset of the Proterozoic samples. Yes.
And I wonder if subsequent hydrothermal alteration, like apart from the mantle metasomatism, would be a concern for your samples.
Not really. That's why the lutetium hafnium system is so great. The diffusion of both lutetium and hafnium normally is incredibly strong, and then hafnium is really, really immobile. So hydrothermal alteration is not going to mobilize it and move it away from the garnet. So that's not really a problem.
Cool. Thanks. Do we get more questions from the audience? I saw some very nice compliment from the chat. So Kira, great talk, well presented for such a complex topic.
Thank you.
Hey, Kira.
Hello.
Hello. Oh, thanks. So that was a great talk. Actually, it's a very interesting study, and you've got a nice sample. And the samples that you presented of peridotites, hasbigites, lazuli,tes, and orthoparoxenite. You had a slide with the episodic metasomatism,
Mm-hmm.
where you show the chromium calcium space of your garnet's composition
Yep.
from the lazulite. I actually saw like some nice trends of your from your hasbigite samples.
Mm-hmm.
They like trends from the G10 space
Yeah.
to the G9 space, you see.
Mm-hmm.
So I'm just wondering if is there a relationship or like a change of those major elements? Is there a relationship with have you noticed like some change in those garnets in also in the trace elements, like in rare earth element distribution?
Oh, that's a
I'm not
great
sure.
question, Gary.
Have you checked that?
Yeah, Gary, can I share the screen again?
Yep, sure.
Let me see if it's gonna be the same kind of disaster as last time. Okay. Which screen are you seeing right now?
That is fine.
Mm,
We can see your slides.
it's slide
Okay.
37. It's slide 37 that I was talking about. Okay.
Okay, so this is all of the rare earth elements plots for all of the
Mm-hmm.
samples because we didn't discuss all of them in the detail.
All
So
right.
that's the one that's the really depleted sample with garnet solutions. The
Okay.
other Heisenbergite samples, they have this really pronounced sinusoidal rare earth element spectra, which is
All right.
often associated with a sort of metasomatism over fertilization to cause that
Mm-hmm.
hump in the middle rare earth elements.
So, okay. So, yeah, I wanted to ask is that attributed to like an ancient metasomatism, like the very, very initial stage of the metasomatism, maybe from the infiltrating malts, from
Yes,
the
so that kind of pattern has to have formed before
Mhm.
the age that we obtained from the garnet, because you can see that this hump, it would mobilize all the rare earth elements and would
Yeah,
mobilize the heavy rare earth elements as well, meaning that it
yeah.
would mobilize hafnium and lutetium alike. So
Okay.
that must have predated the age that we get, or probably occurred at the same time.
All right. Okay, yeah. I think, yeah, I kind of see what which I think I expected because you have like this trend, yeah, the strongly depleted pattern. You see the blue trend,
Yeah.
yeah, and then the also one have got some nice smooth sinusoidal pattern. I'm not sure
Mm-hmm.
if like would you attribute that to some like metasomatism which could have enriched those garnets in heavy rare earth elements.
Mm-hmm. I'm not sure I can speculate fully on the exact kind
Mm-hmm.
of metasomatism that would produce that. This
Okay.
pattern is a little bit more clear. This is the
Yeah.
evolution, just
Yeah.
inherits
All
the
right.
depletion
Yeah.
or depletion.
Okay.
But this one can be many things.
Mm-hmm. All right. Yeah, I see that. You probably have been speculated that, but yeah, I was I was really really interested in this metasomatism.
Mm-hmm.
Yeah. So yeah, that's just what I wanted to understand. There's also like some work that made a paper that I'm working on. So I'm trying to explain
Mm-hmm.
this episodic metasomatism from
Mm-hmm.
the one of the garnets from the Calvary Craton is the oldest kimberlite.
Mm-hmm.
So yeah, that's just what I wanted to understand. And also you've got this nice trend that my garnets as well have got this kind of trend. So I just wanted to
Mm-hmm.
understand your explanation on episodic metasomatism, of which I think this is gonna be helpful as well.
Yeah, there is, I mean, I can speculate on that, which is not fully based in all of the data that I have. But if you consider, like, if you don't assume any subduction happening in the Archean, the other way to refertilize that mantle would be the eclogitic drips. Like, you know, the residual alkali from the TTG formation. If that drips down, that can refertilize the mantle with the necessary silicon aluminum, and that can be the cause for that earlier Archean episodic
Yeah.
metasomatism, like those downward drips of the eclogites.
Yeah. Sounds great. Interesting. Thank you. Thanks for that.
You're welcome. Thank you so much.
Sure. Yes.
Okay, if there's no more questions from the audience. Thank you, Kira. It was great talk, and thank you for answering the questions. This is the end of today's section, and thank you everyone for attending. You're welcome to stay behind for a chat, and we encourage you to turn on the video if you're convenient.